Alright, good morning children. So as a part of the online learning exercise, today we are going to start with the first physics chapter, that is for the 10th standard, that is force. As you can see, just in order to save a little time in the explanation and just so that you understand the things more clearly, I have listed down a few things in the beginning of the chapter. The name of the chapter is force. So what all are we going to study first? That is what I'm going to explain just now. Force. What is force? We have already had an idea, a little bit of an idea about force. It's a physical quantity that basically creates a number of effects on a body. So first we need to understand who applies force and is it applied on a particular body, on some object or something. So the first point that we need to understand is that there will be a person or a body or anybody for that instance who will be applying the force, and he will be applying it on an object or another body. So there are two bodies into consideration whenever there is a force in question. So the basic understanding of this vector quantity, as you can see, force is a vector quantity. We already know it has a direction also, so it will be defined or classified under a vector quantity. So force, what does it do when it is applied on a body? It can produce a number of effects. So the effects of force we'll study. As you can see over here, the effects of force, it depends on what type of object the force is applied on. So if we are applying the force on rigid bodies, what do you understand by rigid bodies? Rigid bodies, those that are solid, that they cannot change shape or size. Okay, so hard bodies, rigid bodies. So as you can see, the force can make them move, or they can also stop a moving body. So I'll give you particular examples to understand the effect of force on rigid bodies. Now rigid bodies, let's say for example you take an iron ball in your hand, you try to press it. So what are you doing? You are applying a force. You are applying that force on that rigid body, that iron ball that you have. So do you imagine it will change its shape or size? No. So that effect of force is not present on rigid bodies. So what does that force do on a rigid body? So you can have an example of let's say putting down that ball on the ground or on a table and then giving it a small push. So what will you observe? You will observe that that particular rigid body starts to move. So earlier a rigid body that was in rest position, on the application of the force it begins to move. So this is one effect of the force on the rigid body. Then another one, suppose there is a body that is coming towards your way, a ball that is coming towards your way, and you apply some force in the opposite direction. So in this case what is going to happen? The ball that was coming towards you was already in motion. So when you applied the force in the opposite direction, you will either stop the body or you will reduce the speed with which the body was moving. So you can make them move or you can stop already moving body. So that's the effect of the force on the rigid bodies. Now coming to the non-rigid bodies, let's say for example that smiley ball that you have, the exercise that we do with that sponge ball that we have. You take the sponge ball in your hand and you again apply that same force which you had applied to the iron ball. So in this case, since it's a smiley ball, it's a sponge ball, you will see that on the application of the force, it will change its shape and size. So does it mean that in case of non-rigid bodies, the effect of force is only to change the shape and size? No. You place the same smiley ball, the same sponge ball on the ground or on the table and you give it a push in one direction, you will see that it can move also. So as you can see, I have listed over here, effect of force on non-rigid bodies. Number one, it can make them move, it can stop a moving body, or it can cause change in shape and size also. Please remember the condition in case of a non-rigid body. Had it been a rigid body, the shape and size would not change. So these are the effects of the force. Now coming back to the types of forces. Now types of forces, we have the contact forces and the non-contact forces. So just now I already gave you an idea that for the application of force and for the result of the force to take effect, we have to have two bodies. One which will apply force, one on which the force will be applied. So there are two bodies in question. Now, what do you understand by the contact forces? Contact forces are those that actually require the real physical contact to be established between the two bodies. So for example, let's say if we have here I have listed the example also. So example of the contact force is frictional force. As you already know that let's say for example this is a flat surface, and then there is a body that is being moved. Okay, so we have applied a small force F over here, and we are moving this particular body. Now, since this body is in contact with this particular body, what are the two bodies that we have over here? Now you see, this is one body, and this ground, this surface is the other body that they are in contact. So there will be a small frictional force that will be acting in the direction opposite to the motion. So what's the direction of the motion? The direction of the motion is this. Why? Because you are pushing the body in this particular direction. Where is the frictional force acting? What is the direction of the frictional force? Opposite to the motion of the body. The motion of the body is to the right, frictional force is to the left. Now this frictional force is an example of the contact force. Why? Because this frictional force will only act if this body and this ground, that is the other body, they are in contact. You cannot imagine the frictional force to be existing if this body is not in contact with the ground. So obviously such forces require contact between the two bodies. Another example you can give is let's say a very practical example, a real life scenario in which you want to push something. You want to push something so that it moves. Now you cannot make that body move until and unless you use your hand or your leg or your body to come in contact with that other body to push. Okay, you can't just stand 1 meter apart from another body and expect it to move. Say that you move and it moves. No, it doesn't happen that way. So contact forces, the two bodies in question, they need to be in contact. They need to touch each other, get into contact. Now the second type of force that we have is the non-contact force. So for the application of such forces, for the effects of such forces to take place, there need not be the physical contact that we spoke about in the first part. So another example is essential for you all to understand: electrostatic force of attraction. So what is this electrostatic force of attraction? We have all studied in our previous classes. You take a positive charge and you take a negative charge. Is it really necessary for you to bring those positive and negative charges in physical contact for that attractive force to come into effect? No. You can place a positive and a negative charge. Let's say for example here we have a positive charge and here we have a negative charge. It's not necessary for you to bring them so that they touch each other. You just bring them close enough and you will feel that they are attracted to each other, okay, without that actual physical contact being made. So that is what we classify as the non-contact force. Another example in this case would be the magnetic force of attraction or repulsion also in that case. So it may also be electrostatic force of attraction as well as repulsion. So I hope that you've got a basic idea of the effects of forces on different kinds of bodies and the types of forces that we have. Now, coming down below to the motion that was created because of the force. Now, motions can be of different types and kinds. So, you see, I have already highlighted these two important kinds of motions that are produced. So, you have one is the linear or the translational motion. The other one is the rotational motion. So, linear, as the word suggests, it is in a straight line. So this kind of a motion, obviously this motion is a result of the force, it is an effect of the force. So if you apply a force, now I have drawn a diagram over here, this will help you in understanding it in a better way. Linear or translational motion. So the motion will be in a straight line. Now you see, this is a flat surface on which again there is a body that is kept and there is a force being applied. So now this dotted line and this direction basically shows that this body is moving towards the right hand side. Okay, so it is moving in a straight line. This is what is known as the linear or the translational motion. Now coming to the rotational motion, which is extremely important from the point of view of our syllabus in as far as this chapter is concerned. Rotational motion. Now when do you have rotational motion coming into play? In bracket, if you can see, if the body is pivoted at some point. Pivoted, basically the word pivot means if you fix a particular point, if you hinge a particular point. So you can, it's better to be understood using this particular diagram. You can see, have a look at this diagram first. Now this is a pulley that I have pivoted at this point with the help of a metallic portion over here. As you can see, this is that metallic portion and it is bolted over here with the help of an iron nail or something. Okay, so this is basically a pulley that we have. Now it is free to rotate. Please understand that this is free to rotate. The only point is that because of this metallic portion and this pivoted portion, this fixed portion, it cannot go down or up or move left and right. The only thing that it can do is on the application of a force. Now you can see there is a force F that I have drawn in the diagram over here. So this force F is acting on the pulley on the left hand side. So what effect will this force F produce? Can it change the shape and size of the pulley? No, it's a rigid body, so it will cause motion. Now what kind of motion? The pulley will, you can see the direction, this is the direction in which the pulley will rotate. So is the pulley moving? Yes, it is moving, but not in a linear or a translational way. It is rotating, it is undergoing rotational motion. So this is the example of the rotational motion. Now obviously you can also have a number of practical real life scenarios in which you can have linear as well as rotational motion in play. Like for example, you can take a ball and roll it on the ground, so it is also moving linearly as well as it is rotating. So this is as far as the types of motions that are produced is concerned. Now very important in physics, always we have units to take care of. So force is a vector quantity. Now we are coming down to the units of force. Now very important, again as always, the SI unit of force and the CDS unit of force. So the SI unit of force is Newton. Most of you already know that it is Newton, and the CDS unit is Dyne. In 9th standard also you have studied. So let me just give a brief revision of how did this unit come about. So you see, in the 9th standard there was a formula that we had studied under Newton's second law of motion. We had studied F is equal to m into a. So this is the force, this is the mass and the acceleration produced in the body. So F is equal to ma was the formula that we had studied in the 9th standard. So now you see, what is the SI unit of mass? The SI unit of mass is kg. What is the SI unit of acceleration? The SI unit of acceleration is meter per second square. So now if somebody asks you, using these SI units in the formula, can you get a unit of force also? So my answer would be yes. Using this formula, I can say that force has a unit of kg meter per second square. It is this that we translate into Newton. Okay. So if somebody asks you now, what is the SI unit of force? So SI unit of force will be represented with a capital N, which stands for Newton, and as you can see, this is that entity that has been translated into Newton. Similarly, now once again I'm going to write the formula for force, which is mass into acceleration. So this time we are going to have a look at the CDS unit of mass. So CDS unit of mass is gram or simply G. What is the CDS unit of acceleration? It is going to be centimeter per second square. So now if somebody asks you, can I represent the unit of force also with the help of these two CGS units according to the formula? Again my answer would be yes. So F, according to this formula, if you write in terms of units, it will become gram centimeter per second square, and it is this that is translated into done. So in effect, units of forces, SI unit is Newton, CGS unit is dyne. Where do these come from? So they come from the same formula, mass into acceleration. Mass SI unit kg, acceleration SI unit meter per second square. Combination of them gives kg meter per second square. This is what is translated as newtons. And similarly over here in terms of CGS units, gram per centimeter square. So gram per centimeter square is translated as dyne. So just to write this more clearly over here, you have Newton and you have dyne. Now what are these? Once again, Newton is the SI unit of force and dyne is the CGS unit of force. Now there was a question, there is this question usually that comes, how do you basically establish a relationship between 1 Newton and 1 dyne? So you see, 1 Newton, I had already discussed that this Newton is translated from kg meter per second square. Okay, and I had already told you that dyne was translated from gram centimeter per second square. So now if most of the students already know that 1 Newton is equal to 10 to the power 5 dyne. Now my point is, how do you come to this relationship? How do you know? You can just open a book and learn this up also, but then that's not the proper way. We should understand how did we get 1 Newton is equal to 10 to the power 5 dyne. Where did this 10 to the power 5 come from? So it is going to come from this same relationship that we had. Let us start with kg meter per second square. Now I am going to try to convert this into gram centimeter per second square. So 1 kg, if I convert 1 kg into gram, it will be 1000 gram. We all know that. Now next thing that we have to convert is meter. What is it to be converted to? It is to be converted into centimeter. So 1 meter is equal to 100 centimeter. Now second square and second square, they have to be same. They do not need any conversion. So we write it like this. So this becomes 1 kg meter per second square is equal to, now you see how many numbers do we have on the right side. This is 1000, this is basically 10 to the power 3 multiplied by 10 to the power 2, and we have gram centimeter per second square. So effectively you have 1 kg meter per second square. By the indices rule, this will become 10 to the power 5. 3 plus 2, as you know in indices, if the bases are same, the powers will be added up. So 3 plus 2 becomes 5. And obviously here we have gram centimeter per second square. Now what was this? This was nothing but 1 Newton is equal to 10 to the power 5. Now what was this? This was dyne. So this becomes dyne. So this is how we have got this relationship. 1 Newton is equal to 10 to the power 5 dyne. So if this question comes for 2 marks in section A, this is what is supposed to be done. We just cannot write this relationship directly. Now what are the other units? The other units include we always, apart from the SI and the CGS units, we have other units which is basically the gravitational units. We have the gravitational units, and in that we have kgf and gf.